scientists, you guys should be on your reading quiz number 11, and I thought it might go over chapter 16 with you. This weather stuff can get a little complicated. Let's take a look at the schedule. So you have chapter 16, 17, 18, your reading quiz, and then next week, week of July 20th is your last reading quiz, and then your critical thinking exercise will be due. And I will post the critical thinking. What you're going to do is you'll pick from a topic, and then you'll answer 9 questions and submit those. And so I will upload that into your content. Okay, chapter 16, the atmosphere, composition, structure, and temperature. Basically, this 16 kind of sets you up, and when you study the weather, you're really studying weather. You're really studying thermodynamics. So you need to know the difference between the weather and climate. And the weather is what you're going to wear today, but the climate is what jackets you don't have in your closet. It's a longer term. There's major gases in the atmosphere. I'm sure you're familiar with oxygen, but you need to know the major gases. You need to be able to look at a graph and take a look at the air pressure and be able to sketch and label that as the atmosphere, just like the earth, has layers. So you need to be able to sketch those different layers based on temperature, whether the temperature is going up or down. And it's super important to understand the Earth-Sun relationship, because that's our major source of our energy here on Earth. So it's important for us to know about the length of daylight and just the relationship that we have with the sun as we go around it. You need to know the difference between heat and temperature, and how heat can be transferred, like latent heat, the hidden heat. And be able to just sketch out and label a diagram that shows all of the incoming paths of radiation and what happens to it. And there's 5 commonly types of temperature data that we use to interpret temperature data on a map. And isotherms are just lines on a map that equal temperature. And then you need to know the principal controls of temperature and use examples to describe their effects. So like, the temperature of the sun when it hits the equator, gets the full belly of the sun. And then you need to know how to interpret the patterns of world maps when you're looking at July or January. So have an understanding that weather is short-term, climate is long-term. This is what's called a climograph, and it has the month on the x-axis. You can see the temperature in degrees Celsius or degrees Fahrenheit for me on y-axis. And this shows the average lows in green, the record lows in blue, the average highs in yellow, and the record highs in red for any given location. And I invite you to Google it. If you want to know what the temperature is going to be in Cancun, you can Google it. Google will bring up, and you can pick graph, and it'll show you what the temperature will be like annually by month in Cancun. So I will do that. All I did was Google Cancun annual temperature, click on the graph, there's the climate graph. So the lows in July are 76 degrees Fahrenheit, the highs in July are 90. So it gives you kind of a range. It also gives you the amount of daylight. So in June and July, Cancun's in the northern hemisphere, you get the most amount of daylight, 13.5 hours, versus January, December. So that's pretty obvious. If we look at Sydney, Australia, you'll notice the graph is inverse because they're in the southern hemisphere. So when we're having our summer in the northern hemisphere, they're having their winter. So you'll see the climate graph is inverse what you saw at Cancun. So in July, their temperature is ranging from 47 to 63. So you'd want to visit Australia and Iowa in the northern hemisphere winter. The elements that make up weather and climate. And these are the things that we measure regularly. Okay, temperature, humidity, how much moisture is in the air, how cloudy it is, if it's raining, precipitation, or snowing. the air pressure, whether it's low, which means bad weather, or high, which means good weather, and wind speeds and direction. So know those 6 things. Those are the important elements that we deal with in the weather. The major gases in dry air are nitrogen, 78%, oxygen, 21%, and just minor amounts of argon and carbon dioxide. So here's a pie chart showing you that. So you should know that mostly the air is made of nitrogen, 78%, and then add the oxygen to it, and you're looking at 98, over 98% of the air is made up of nitrogen and oxygen. Just tiny amounts of carbon dioxide, argon, neon, helium, methane, krypton, hydrogen. And I can tell you that a little tiny bit of water drives the weather. Now this is a monthly CO2 concentration, and it's showing since 1960s when the graph started that even though CO2 goes up and down on a monthly basis, if you average that over the year, you can see the line going up. And during fall and winter, photosynthesis slows, and the decay of plant material will release the CO2, and that'll send the line up. Water vapor only makes up about 4% of air's volume. It's what forms clouds, precip. It absorbs heat energy from Earth, but that little bit of water vapor is what drives our weather. Aerosols are just tiny little fragments, little tiny particles in the atmosphere. And then for the ozones, 3 atoms of oxygen, O3. It's not very uniformly distributed in our atmosphere. It's about 10 to 50 kilometers away from the surface. It absorbs the harmful UV radiation that the sun is emitting. It kind of absorbs that. So if there's human activity that depletes that ozone layer, and we've stopped making those chlorofluorocarbons, the CFCs, then because it was breaking down our ozone layer. So we want to keep that ozone layer because it protects us from those harmful UV radiation. So here is an ozone hole over the Antarctic, and you can see that big purple blob. It's pretty big, October 1st, 2016. So they monitor that. Now, if you go up in the atmosphere in a balloon, the pressure is going to change. Okay, so if you were to rise up in a balloon to the top of Mount Everest, this shows you the pressure on the x-axis, 0 to 1,000 millibars. And then if you go up in altitude up to almost 6 miles, you can see that your air pressure has dropped from 1,000 to less than 400, about almost 300 millibars. So the pressure really decreases. So as the balloon goes up, the pressure decreases and the balloon will expand. And that's exactly what weather balloons do. They go up so far and they expand until they burst, and then they come back down. Now, the atmosphere has layers, 4 layers: the troposphere, the stratosphere, the mesosphere, and the thermosphere. They are separated by the tropopause, the stratopause, and the mesopause. You can see the red line is temperature, so the temperature is decreasing. It's getting colder as you go up to the top of Mount Everest, but for some reason, right at the tropopause, it inverts, and then it starts to warm again. That's why those cumulonimbus clouds in the summertime, they go up to the tropopause. They can't rise anymore. Then they become unstable and they rain out. So just familiar with those temperature inversions that separate the tropopause, the stratopause, and the mesopause. All right, Earth-Sun relationships. This is pretty important. The longest day is our summer solstice, and the sun is at a pretty high angle, 73.5 degrees. And this is at 40 degrees latitude, north latitude, a little bit north than Vincennes. So in June, that's our summer solstice, and the sun is highest, and it's the longest day. Conversely, far to the right, our shortest day is the winter solstice, December 21st and 22nd, and the sun's angle is lowest in the sky, 26.5 degrees. And again, we're in the northern latitude. Now, during the spring or fall equinoxes, it's equal. The day and the night are equal. 12 hours a day, 12 hours a night. The sun's about 50 degrees. So we get the most energy on that longest day of the year. It's just like a flashlight. If you hold a flashlight to the table, you get the most intensity from the beam if you hold it straight. But if you put that flashlight on an angle, and this kind of explains why, even though the North Pole gets lots of sun, intensity of the energy coming is pretty low, and that's why it's cold up there. The Earth's axis is always inclined. It's at a fixed position of 23.5 degrees. It's always pointed in the same direction, and that tilt causes the seasons. So you can see as the sun's rays hit the Earth, and in this particular instance, we are in, it's hitting the southern hemisphere, so it's their summer, and then it's obviously our winter because we're not getting as much sun in the northern hemisphere. So the summer solstice, the winter solstice, and the equinoxes are special days. Now take a look at this. So if we start at the equinox in March, you can see they've got the Arctic Circle, the Tropic of Cancer, I remember because a lot of people in North America people get Cancer, the equator, and the Tropic of Capricorn. And so you get equal 12 hours of sunlight, 12 hours of dark, okay? We're kind of to the side of the sun. As we come around, because of that tilt, in June, the northern hemisphere, we are tilted toward the sun. That's why we enjoy our summers. We're tilted, we get more sun, we like to boat, get out on the lake, we get a lot more heat. Then we come into fall, and we've got 12 hours of daylight, 12 hours of nighttime at the September equinox. But then at the winter solstice, we're tilted away from the sun, so it's cool. It's colder here. And then the southern hemisphere is tilted towards the sun. So that's why they have their summer and our winters. If you take a look at this graph, you're again looking at the two solstices and the spring and the fall equinox, and it's just telling you the number of hours of sun that you get. So in June, we get up to 15 hours of the sun's rays, versus in December, we're only getting about 10 and a half. Our days are shorter. But again, during the equinoxes, the spring and the fall, 12 hours of sunlight, 12 hours of darkness, equal. Now, here we switch gear a little bit. Heat's always transferred from warmer to cooler objects, and this is good news for the Earth, because the equator is moving the warm air to the poles. And thank goodness, or it would be super hot, maybe not even livable at the equator if we weren't moving that heat. And the mechanisms that you can move heat are conduction, convection, and radiation. And this is just a pot of boiling water. So the conduction is what you feel, the convection is the water swirling around, and the radiation is the heat coming off the charcoals, and I'm sure you felt that when you're up near a fire. Now radiation comes in different wavelengths. The gammas are the short waves, those are the ones that hurt us. The long waves don't seem to bother us, the radio waves. And then we've got some visible light. And the laws that govern radiation, hotter objects radiate more total energy. Seems obvious. Hotter objects radiate more energy as short wavelengths. So you've seen this. This is the electromagnetic spectrum. And you can see the short waves on the left. They're only 0.001 micrometer or micrometer when you measure the wavelets. But then long radio waves are over on the right. And visible light falls between ultraviolet and infrared. So how much energy is coming in? And we call the sun's energy solar radiation. So if you have 100% of it coming in, 50% of its direct and diffused radiation, it's absorbed by the land or the sea. 5% gets backscattered to space, and then 20% hits the clouds and heads back, and so you get 30% lost to space, 20% gets absorbed in the cloud, and about 5% is reflected from the land sea surface. Albedo is just a measurement of reflectivity. So I always tease the dean that he has a lot of albedo because he's bald, and so when he's walking outside, he's reflecting a lot of light back. But a wet cloud field, has an albedo of 15 to 25%, versus asphalt, which is absorbing a lot of that, only 10%. Water can vary with the sun angle, it can be highly variable, 5 to 80%. Snow has a very high albedo, 50 to 90%. So if you have a lot of pavement, urbanization, it affects the albedo because you can see wet cloud and forest can even be down to 5%. There's a greenhouse effect, I'm sure you've all heard about it, and it's basically just this model that, when when we've got the energy coming in and all the long wave energy is radiated back to space, but if there's any kind of gases or anything that get it trapped, then we can start to heat things up. Now, air temperature is a complicated data set. You know, there's maximums, minimums, average, daily means, daily range, a monthly mean, an annual temperature range. It gets pretty complicated. But if you're looking at a map, an isotherm is just a line that's connecting areas of equal temperature. So here's the isotherm. So if you look at Milwaukee, it's 52 degrees Fahrenheit, and that 52 degrees is just north of Topeka. And these isotherms grab everything that's less of it is to the north, and everything that's more of it is to the south. So you can see that, and if it's exactly the same, then the line will go directly through it. And I do not see any falling right on the even. Vegas is closed at 59, but they picked their contour interval to be 10 degrees Fahrenheit. And then they color the map, and this is what you'll see a lot of times on the news. Now, land heats up more rapidly and to higher temperatures than water. And water has this weird thing, it has a high specific heat, which is the amount of energy it's needed to raise a temperature from 1 gram of a substance, 1 degree. So it has a high specific heat. And the example I like to give is I used to work at a Bloomfield pool. And when you get there in the morning, you know, the concrete was cool and the pool had cooled off. But pretty much by 11 or 12, the concrete was hot. Water was still cool, but by 2 or 3 o'clock, the concrete was hot and the water was warm. And especially at night during the pool party, then the concrete would cool off, but the water would still be really warm. So the concrete would heat up much more rapidly, and the water would hold the heat, but then probably about 1 a.m., then it would turn and it would start to cool off, and then it would be cool in the morning for the swimming lessons for the kids. So you get this differential heating of land and water, and the northern hemisphere has more land than the southern hemisphere, so you get more of this heating. Now this shows a monthly mean temperature for in British Columbia versus Manitoba, and again, you know it's both northern hemisphere because it's warm in June and July. You can see their location. Vancouver's near the ocean, so it doesn't have as high, it doesn't get hot, it doesn't have as much of a range, where Winnipeg is further inland. So it's getting hotter and cooler. But the ocean is tempering the Vancouver temperature, so it's not as hot, or cool, which is common. Now, Concepcion and La Paz in South America, now this is an example of 2 locations in the southern hemisphere, but La Paz is in the Andes Mountains. So because it's at a higher elevation, a higher altitude, then it's colder there. And you know you're in the southern hemisphere because it's cooler in the summer. So the geographic position controls temperature, not just altitude and location to the ocean, but also the windward coast and the leeward coast. So Eureka, California is on the windward coast, so it has more of a tempered climate, not as hot or cold, where New York City has more of a high, and because it's on the leeward coast. Cloud cover and albedo. The clouds reflect the light off. So if you've got a clear day, it's going to get hotter and cooler. But if you have an overcast day, it kind of squishes that curve where it's not as hot, or cool. So the world distribution of temperature, we can look at these global maps of temperature and global temperature patterns, and we're just going to look at isotherms again, and we want to compare January to July. And so we're going to look at the southern hemisphere. The isotherms are straighter and they're more stable in the southern hemisphere. And the annual temperature range is small near the equator, but it increases with an increase in latitude. So when you look at the January world sea level temperatures, you're in January, you can see these red blobs up over the land masses and how the land is affecting the temperature. And then when you look at July, you see that thing shift. Obviously, it's much hotter up around the equator, getting a full belly of the sun. So that's pretty much it for Chapter 16. On the weather and the climate, I highly recommend that you read the chapters and that you do the end of chapter study quizzes. And those are great to do because you can see the answer right away before you jump into your other quizzes. So that's chapter 16, and if you've got any questions, make sure you email me. Thanks.